You guys are actually going to learn something in this video. It's going to be pretty sweet. Today, we're going to be writing a Linux daemon / service, whatever you want to call it. It's essentially just a program that runs in the background for a long period of time without user interaction. They're pretty cool. They're pretty popular too. Like, I've written some for myself, for friends. I even wrote one for my ex-girlfriend, which is a bit yikes, but anyway. Today, in under 200 lines of code, you're going to learn about shell arguments, exit codes, blocking I/O operations, system calls, and a sprinkling of dynamic memory management. It's going to be pretty sweet. Let's dive right in. We're going to be writing our daemon in C. If you haven't done any C programming before, that is totally fine. As long as you have done some programming before, you can use the knowledge that you have from that language to follow along with what we're doing here. We're not going to be doing anything crazy. If you haven't done any programming before, feel free to stick around. However, you may want to just refresh yourself with some pointers, no pun intended guys, before we get started, because this is going to be a reasonably technical video. The next step is actually going to figure out what our daemon is going to do. And this is kind of hard, like, you know what they said, it's like 98% inspiration, 2% perspiration, or whatever the dumb quote is. But yeah, like, we're going to figure out what the daemon's actually going to do. So I've come up with an idea for you, but if you're going to be writing your own, you can copy this, but you might want to come up with your own to make things a little more interesting. What we're going to do is write a daemon that watches a file on the system and sends you a desktop notification if that file is accessed or changed. Now, full disclosure, I have actually gone ahead and written up the program here beforehand just so I can get an idea of how it's going to fit around, but in this video what we're actually going to do is I'm going to start from scratch, and we're going to go through my process of how the program actually comes together, which I think is going to be pretty cool. Now that we've identified what our daemon is going to do, we've got to figure out what libraries and system calls we're going to use to actually get that done. And this is where one of the key concepts of systems programming comes in, which is system calls. Now, if you don't know what a system call is, it's like you've got, for example, your C standard library calls. It's like that, essentially, but for the platform that you're on. So Linux, if you want to interact with any Linux-specific APIs, like, for example, Filesystem Events are handled by the kernel. If you want to interact with any of that, you're going to have to do a system call, which is where you basically ask the kernel, hey, can I get this information when I want it? And it's platform specific, right? So you can have Linux, BSD, Windows, Mac OS function calls, and they can differ depending on the system that you're on. So to figure that out, just go ahead and grab up your web browser. And on the right over here, I've already gone and figured out what we all need, but I'll show you how to do it. So the first thing we want to do is like desktop notifications, right? So we just search up like Linux desktop notification library. And you can see here there's a Python library that comes up. We're going to ignore that. We don't want that. Here the Arch Wiki has desktop notifications as a thing. So let's have a look. And the first thing that pops up is libnotify. Now, if you're on any mainstream desktop environment, you're going to be using libnotify because GNOME and KDE and XFCE and everything, they use libnotify to serve you desktop notifications. If you're running something custom, you'll know what you're running. But if you're on any mainstream thing, it'll be libnotify. So what we want to do now is literally just go back and say like libnotify API. And here you go. The first result is the GNOME developer website. And we go to the notification API right here, and we got all the calls we need. That Arch Wiki page, by the way, if you scroll down a little bit, it actually does have examples in a couple languages. So here's the one for C, and we're going to be using this one here with libnotify as the dependency. So now that we found out our desktop notification API, how are we going to get file system events? Like, you know, we want it to be when it's open, change, whatever. So we're just going to look up like Linux monitor file system activity. It's fine. And these results are not exactly what we want, so we might change that to events. And here, SSH file system monitor, we don't care. How to monitor, blah, blah, blah. And this is what we want, the Linux man page. So you look at this man page here, and you'll notice that it says, I notify monitoring file system events, which is exactly what we want. And here it says the following system calls are used with this API. So the Linux manual pages essentially contain a reference for all of the system calls that you might want to use in your programs. So when you're on these, when you're looking for this stuff here is garbage, this stuff here is garbage, this is what you actually want, because this is the actual documentation for the API. So like a skill as you get better at this stuff is definitely like finding things that you actually need on Google and things like that. And the Linux man pages, if you're on a Linux system already, you can just use the man command to find them. But this is just more like a general, how do you actually go out and find this information? But yeah, here we go. Here we've got all the system calls that we're wanting to do. Another issue I have, maybe you get the same, is like coming up with a name for your projects. I always find that harder than actually writing the code themselves, because it's the first thing you're gonna do. Like, you're gonna make a folder and call it something. What are you gonna call it? I like to come up with kind of clever names, so I've chosen Rolex Hound. And the reason I've chosen Rolex Hound is because there's a concept in systems and embedded systems called a watchdog, which is essentially just a little guy that watches for issues in, like, faults in your program, and it can restart things and trigger interrupts and things like that. But I've stretched that definition a little bit here because we're going to be making a watchdog for file systems, and then I just decided to call it something dumb like Rolex Hound. So yeah, that's what we're going to be doing. So when I start a C program, I just include all of the headers that I think we're going to need. We're definitely going to need standard IO, alright, that's a given. We're going to need standard lib, we're going to need unistandard, and as you're writing your, not unistandard IO, just unistandard, as you're running your program, if you come across libraries that you've included that you don't need, you can just remove them later, that's fine. I usually like standard bool, just true false instead of 1 0, makes it a bit easier to read. And we're going to need standard int. And now all C programs start essentially the same way, int main. And we're going to do something here called, I'm going to go over exit codes. So when your program exits, right, and this is important for system and terminal utilities especially. When your program exits, it returns with a code that lets the operating system or the shell know, was this program execution successful? And when programs encounter an error, usually they'll return a non-zero exit code. So 0 is kind of like success, right? So your program should normally, exit with 0. So what I'm going to do is hash define exit code success as 0. And we can go ahead and replace this. And if you're not familiar with hash defines, essentially it says, whenever you come across this, replace it with this. It's pretty simple. It's like a constant, but not really. Because it does it before compilation, which is cool. But anyways. So now, let's think about how we want our program to work. What I want is for you to execute it like this. I do Rolex Hound, and then path to file to watch. That's what I want, okay? Now, in C, to get access to shell arguments, you can pass them into main like so. So argc is the number of arguments, and argv is the actual arguments themselves. Now in C, the program name is included in the list of arguments. So argv 0, like the start of the argv array, will always be the program name usually, and then from there, you got stuff like that. So this is going to be a very stupid argv handler because we're just doing a very stupid application. I'm going to go if argc less than 2 exit, and we're going to do a failure. So I'm going to do hash define exit error too few args as 1. And we're going to print a usage statement as well. So I'm going to go print to standard error. Now, standard error is where you want to print your errors to. Standard out and standard error are, you can both see them when you execute it in terminal, but it's best practice to print your errors to standard error, so I always do that. And I'll just print out like usage or Rolex Hound path, and then we'll exit. And now from here we can say that our, we've always got this argument here. So that's going to be the path to our file that we want to watch. So what we're going to do, and this is where the sprinkling of dynamic memory management comes in, and I'll show you why in just a second. What I want from this program, in the corner, it's going to pop up with a notification. It's going to say the file name, and it's going to say this file was something. Modified, opened, deleted, whatever. So now, Rolex Hound is given the path to the application, but how do we actually get the base path of the application, the file? So how do we get the base path of the file itself? Because I don't really want to have in my notification /blah blah 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 blah, the entire file name and file path, sorry, in my desktop notification because that'll look really dumb. So you can use strtoc in C, which basically tokenizes string. Now, for fair warning, this is not thread safe. We don't care because we're just using a single-threaded application. But you want to use strtoc R if you're doing a multi-threaded application. So anyway, I'm going to define a character pointer called base path. And the reason I'm going to do that is because strtoc is destructive, meaning that whatever string pointer we pass in, it's going to modify. And I don't want my argv being modified, really, because I want to use it later. So what we're going to go ahead and do is say that base path equals cast of malloc size of car times strlen of argv1 plus 1. Okay, wow. What's this? Oh, I also need to include string.h. Like that. Wow, what does this do? So, this is where our sprinkling of dynamic memory management comes in. Malloc essentially just allocates an amount of memory on the heap for the thing that we want to store, and it according to this size. So we've done size of a character, because a string in C is a collection of characters, times the length of the argv1 argument, which is what we're storing, plus 1. And the reason I've got the plus 1 at the end is because strings in C are terminated with a null character. Now we can actually strtoc it. So what I'm going to go ahead and do is add a token up here. And we're just going to go ahead and say token equals strtoc, pass it our base path, and we're going to do a / because the idea of this, remember, is to get the file name at the base. So essentially we're just trying to tokenize this and go to the very end of our path that we've been passed in. So now we can do this while token not equal to null, base path equals token equals strtoc null, like that. Oh, and my lights changed. That's fantastic. Sorry guys, they're on a timer. They're on a timer. Anyway, token not equal to null. So until the end of our token, we're going to set this. So base path is equal to the previous token, and then we find the next token. So essentially we're going to be leapfrogging with our base path until we get the end. And if we go ahead and print this out real quick, printf%s \n of base path, you'll see when we go ahead and compile this that it's all good. So what I'm going to go ahead and do is gcc rollxhound.c-o rollxhound, of course. And it actually turns out I've got a new line up here. It's a good catch, good catch. So, rollxhound, and I'll just be really meta and do rollxhound.c. And so as you can see there, we passed it this, and it does that. If I do the whole path to rollxhound.c, I'll show you that that works as well. And as you can see there, we just get rollxhound.c. That's the point of this line here. Now we've got the base path of our file. And argv1 is unharmed. How good. So, the next stage of this program is essentially when you write daemons, the point is that they run pretty much forever, right? So you're going to want to do a while true loop. And now what you'll notice here is that unless we have a break condition, this exit success is never actually going to be hit. So we can go ahead and get rid of that because in this daemon, we're actually never going to break out of this main loop in our main function. The way that we are going to go ahead and do that is with signals. And so now it's a good idea to go up ahead and include signal.h, because basically what we're going to do is when we Control-C this program, we're going to catch that and shut the program down correctly and then exit with a 0 exit code, essentially. So we can go ahead and leave that there for now and keep that in mind for later. So now, this is where we actually have to get a little bit spicy, because what we want to look at now, we've got the file path that we want to watch. How do we actually watch it? How do we watch it? So go up to the documentation for Inotify, and we're going to have a look. So let's have a look at some of these system calls we've got access to. creates an Inotify instance and returns a file descriptor referring to the instance. We're probably going to want to do that first, right? Inotify add watch manipulates the watch list. Each item specifies the path name of file or directory. That's exactly what we want. So essentially what we want to do is initialize Inotify and then add the file path that we've got to our watch list. And one of the great things about this is that if you go down to the bottom of most of these system call man pages, they actually have examples. How good is that? So let's have a look at this example program and we'll try and understand what it does. So we don't really care about any of this stuff. Essentially what's going on here, we'll go to the main. They've done the same thing, right? Like they're just going to use argv, really basic. So Inotify init 1. Now this is where the concept of non-blocking versus blocking operations comes in. If you scroll back up to the top, you'll notice that init1 has a flags argument. So if we go ahead and have a look at this, what flags can we actually set if we want? So non-block is one of them. So what is blocking when it comes to IO operations? Essentially, when your program is running, right, like if I've got this program right here that's doing while true, and what we're going to be doing is maybe like, you know, a equals read file path or something like that, and we're waiting for something to happen. A blocking operation is where the program hangs on this line right here before it gets the event to continue. A non-blocking program will continue its operation, like it checks this. If there's nothing available, it'll continue its operation until something is available, and it can do other stuff as well. What we're looking for in this daemon is blocking. Okay, we want to block. So essentially, we're waiting for an event to happen, and we don't care about doing stuff in the background. But non-blocking versus blocking is a very important concept in systems programming in general, because you can design the entire architecture of your program changes depending on what you need. So we don't actually care about specifying these flags, so we're going to use Inotify init, just the regular one. But let's go back to this example program here. And you can see they check an error status. So what we're going to do is go up to their include, and we see we need this one right here. This is going to be our header file for Inotify. So going back to our application, we're going to go ahead and hash include sys Inotify. And now we can actually go ahead and initialize our notify. What I'm going to do is actually make this file descriptor for the Inotify instance global. And the reason I'm going to make it global is because when we receive a signal, we want our program to clean up correctly. So our signal handler is going to need access to this. Now, global variables are kind of a hotly debated topic. I think they're fine as long as you handle them correctly. Now, we're doing a single-threaded application that's under 200 lines of code. Global variables, the argument for them being kind of like hard to figure out where they're used doesn't really apply here, and it just makes our life a whole lot easier. So I'm going to call this iEventQ, and I'm going to initialize it to -1. Now, the reason I call it iEventQ is because if you actually have a look at our, like how we're actually going to be doing it, that's actually the FD that we're going to be, like when we initialize it here, that's the file descriptor we're going to be reading from for all of our events. So I'm going to call it eventQ because we're going to be receiving from that basically. And so now we can literally just go ahead and call down here, and get rid of this line here, and we'll just go ahead and call iEventQ is equal to iNotify init. And now we're going to go ahead and check the error code. So if iEventQ is equal to -1, print out to standard error, error initializing Inotify instance. And we'll exit with a new exit code. ext error init Inotify. And make that error code 2. So we'll exit with that. So once we get to this point, we assume that, you know, everything is chill and we're all good. So now the next thing that we want to go ahead and do is actually add the file that we're watching to the watch queue. So if you go back to our manual page here, we're going to have a look at this add watch system call. So as you can see, it takes in the FD of our Inotify instance, the path name, and it takes in a mask here. So this is another concept when it comes to low-level systems and embedded systems programming, is the concept of a bit mask. If you're familiar with binary numbers, let me just get up an example here. You'll know that there's a binary number that's like 000000, right? And you can set 1 here, you can set 1 here, you can set 1 here, you can set 1 here. A bit mask is literally just taking this number here as flags that mean something. So when my you might have this as a settings thing. So when this bit is set to 1, essentially what that means is that enables some functionality, and when it's set to 0, it disables some functionality. So that's what a mask is, basically, in very simple terms. And you can do things like with it, like you can AND it with 0b 0 0 1 0 0 0, and as you can see, that comes out to 8. Which if you do like 0b 0 0 1 0 0 0, you can find out that that's 8. So what you can actually do is like something cool. If you want to figure out what flags are set, you can go like 15 and 8 equals 8. I'll just put brackets around this to make sure it's all good. And you can see that that comes out as true. So you can actually use bit masking to check the status of flags, essentially. So let's have a look at, like these two are pretty self-explanatory. Let's have a look at the mask. So the mask here, it says see Inotify for a description of the bits that can be set. So we go back to here, and we're looking for the mask. Here we go. This is the mask field. So we can set access. File was accessed, blah, blah, blah. We'll look for the ones we want. So this is essentially like the events that we want to monitor. So access, definitely. Create, sure. Close, right, yeah, definitely. Delete, sure. Modify, yes, 100%. Open, maybe not. That'll probably spam it. But you can see here, these are the actual ones that we can go ahead and set. So the next thing we want to do with our program, right, is create the masks that we want to do. So what I'm going to do is go ahead and make a uint32 t, and I'm going to call it maybe watch mask. And here is where we go ahead and set all of our things. So I want create, and I want delete, and I want access, and I want close for writing, and I want modify, and I want move. I think it's this one here, and that should be fine. This operator here is the OR operator. So remember when I was telling you about bit masks before? These are their own flags that are set, and when you OR them all together, it combines them essentially. So like if a bit 1 is set in one position, it'll set it in all of them. And that's basically all that's happening there. So now what we can do, and if you have a look at this, go back to this thing here, you can see it returns an integer. That's going to be our, like a status code or something. You can check the return value down here. Returns a watch descriptor, a non-negative integer. So what we're going to want to do now, we go back to here and we say, and I'm going to make it another global. I'm going to say I event status maybe. And we're going to go I event status is equal to Inotify add watch. And here we're going to do our event queue for the first argument. Our file name is in argv1, and you can see why I didn't want to modify argv, because we've got to reuse it here. And our flags are watch mask. So now what we can do, if event status equals -1, fprintf to standard error, adding file to watch instance is fine. And you guessed it, we're going to have to make another exit code. So ext error add watch. Sweet. So theoretically now we're ready to rock and roll. So this is cool, but how do we actually access those events? If you grab the example code that they've given us on the Inotify page, we're going to see what they've actually done here in order to do that. So they set up all of this stuff like normal. They're doing some extra stuff here, like they're doing it for the entire directory instead of just one file. So they're doing some more advanced stuff here, but you can like find the parts that you actually need. So here, this is their while one loop, right? So this is their like Daemon loop. You can see here, if you get a, like if something happens on the file descriptor, they do this handle events thing. So we'll go up to that function call here. And you can see that what they do is for car pointer, blah, 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 blah. This is what's important. So that iEvent queue that we defined earlier, we're actually going to read into a buffer from that, a whole bunch of data. Like it's a stream that we're going to be able to read from. So you can see they allocate a 4 kilobyte buffer, and what they're actually going to go ahead and do is read here into the buffer from their iEvent queue file descriptor. And then here, because a read operation could potentially return more than one event, they're going to loop through all of the events in that buffer. So we can pretty much copy this. I'll explain what this code does when we get to writing it, because it's a bit of a you know, fuck around, but yeah, we'll get into that, so don't worry, I'll explain it all. So we'll go back to our program, and we're going to go ahead and declare a buffer, a 4 kilobyte buffer to store our characters in. And so now down here, I'll just make that a little nicer for you. Down here, what we're going to go ahead and do is I'm just going to do like waiting for iEvent, just so we know where we're at in the program. Actually, sorry, one more thing before we continue. Just in C, it's very easy to not check your null pointers. So just make sure you're checking all the null pointers. And this probably should never happen in the course of the program, but you can never be too safe. So I'm just going to go ahead and define ext error base path null as 4. And we're going to exit on that. Just like, you can never be too careful when writing a C program, and it's very easy to make mistakes and things. So error getting base path. Cool. So here we're going to wait for our iEvent in our main Daemon loop. So we're going to have to declare this integer up here. I'm going to call it read length, because the read command the read function is going to return the number of characters read. So we read length iEvent queue into our buffer, and size of buffer is how many characters we're going to allow it to read in total, so 4096. So now what's going to happen is we're going to copy that really kind of fucked line from the man page, and I'll explain what it does. So it's a for loop car, and it uses a pointer. So I'm going to go ahead and declare another pointer up here called buff pointer for car. Actually, sorry, my bad. They declare it in the loop, so I don't know what I was doing there. But buff pointer for buff pointer equals to buffer, buff pointer less than buffer plus read length, buff pointer plus equals size of struct Inotify event plus, and we're going to have to go ahead and define a struct over here, and I'll explain why we've got to define that struct. Const struct Inotify event, I'm going to call it watch event. I'll call it watch event. If you go ahead and look at our documentation here, right at the top, each successful read returns a buffer containing this structure, so an Inotify event struct. So we're going to need a one for that as well. And what they do in this fucked line here, plus watch event len. So what is going on here? We declare a pointer buff pointer and set it equal to buffer. What we're doing here is we're creating a pointer and we're setting it to the start of the buffer. So our pointer buff pointer is now at the very start of the buffer. Our increment step here, our check step here, is that the buffer pointer is less than the the start of the buffer plus the bytes read, okay? And then our increment step is the buffer pointer plus equals to the size of this struct event plus the previous event's length. So if you think about what this is actually going to be doing, we start our pointer at the very start of the buffer. So at the start of the buffer, our check is that the current pointer is less than the pointer of the buffer plus the length of the total characters read. So we're just checking to make sure that our buffer pointer is not larger than the buffer that we're trying to read. And then our increment step, we've got the buffer pointer, so where we're currently looking at, plus the size of the struct that we're trying to read, plus the previous event's length. So we start from here, we go the size of one struct, and then we go the size of like that struct plus another struct. So yeah, it's pretty fucked, but you get an idea of what it's doing. Essentially, we're looping through the output of that buffer, the output of the read command, and we're assigning a struct to each point because we can read. That's what it returns. It returns those structs. I hope I explained that all right. It's really like a bit tricky, and you kind of have to understand pointer arithmetic a little bit. So I kind of hope that was all right for you guys. But anyway, before we get into that though, we're just going to check the read length equals -1, error state. So standard error reading from Inotify instance. And yeah, we're making a lot of exit codes, aren't we? I hope you guys like exit codes. Read Inotify. I like exit codes. I'm a bit weird. Okay, so now we're guaranteed to have something in the read. So what we can do is essentially our watch event. We're just going to copy again from what these guys do. So in our in their handle message, you can see what they do is they cast their buffer pointer to this struct, and that's like that's fair, right? Like we've set up all of our pointer arithmetic correct. So given that the read command will return those structs, we can just go ahead and cast our pointer to the struct, and it should be completely chill. So we can go ahead and say watch event, which is our struct, is going to be equal to the cast of the Inotify event struct of our buffer pointer. So now theoretically, we're receiving file system events and we're casting them correctly to the struct that we can actually modify and do stuff with. And if you have a look at the struct definition up here, you can see there's this mask which describes the events, which is what we're looking for. And down here in their example code, you can see they can check that with a bit mask, and it determines the status of the event. So now with our mask, you can see we've set up here all of these ones. We can legit just go and check all of those. So we can say if watch event mask and remember I showed you in my bitmask demo earlier, you can use the AND bitwise operator to check flags. What was the first one we set? In create. Now we can do something with that. Because we're going to check a few, I'm going to define another pointer here for notification message. Because at this stage, if we circle back to what we want to do, we want to display a notification to the user about the kind of event that we've received. So what we're going to do is say notification message is equal to file created, maybe. And so we can kind of do the exact same thing for all of our other events. So we did in delete, notification message equals file deleted. We can go ahead and do the mask is in access, and I'll just go ahead and do all of these in cut because it's going to be a whole lot of me typing out these events, basically. Okay, I went and typed out all these events. So essentially you can just see we're setting the notification message accordingly, and the astute among you might have noticed, because it's a bitmask, right, like multiple of these could be set at once, so the notification is going to be the last one in our list that gets, the last one in our if statement that gets checked. The nature of the beast, it shouldn't really happen, but like the astute among you would have noticed it can happen. And now just to be sure, what I'm going to do is up here set notification message to null, because it's a pointer, we can do that. And the reason I'm going to do that is so that we can do this check down here. If notification message equals null, continue. So why would we get a situation like this? We get a situation like this in which our iEvent read has returned an event that we don't care about, that we don't want to send a notification for, because our bitmask here is just checking and setting this accordingly. So what we can do is set this equal to null, and a lot of people, dude, like, listen. If you can't deal with null pointers, it's a skill issue, okay? It's a skill issue. They're useful. They're useful, alright? If you can't deal with null pointers, you're like, oh, null pointer's bad. It's a skill issue. Check that the pointer is null down here. We can not do anything with it because we don't care about that kind of event. Okay. So awesome. Awesome. Let's test to see if that works. Printf %s\n notification message. That's all we're going to do. Now let's go ahead and do our GCC. And if I do this again on xoxo.c, we're waiting for iEvent. How good is that? Now if I go ahead and do this, ooh, peep that, boys. File modified, file written and closed, file accessed. Kate's doing a whole bunch of stuff, who knows what it's doing, but basically you can see that we're, all of our iEvents are triggering right, and we're setting the notification message. That's awesome, dude. So now all we need to do is wire that up to a notification API. Isn't this fun, guys? Systems programming is so cool. You're literally like the coolest kid in school if you can do this. Definitely, 100%. Okay. So let's go ahead and add libnotify to the mix. Now, if you go back to the Arch wiki, you will have noticed that our example right here specifies a couple of things. So the first thing is we need to build it with this GCC command. Like, we've got to include this package config and specify we want to link the libnotify library. And we also have to include this header file. So I'm going to grab this header file and I'm going to stick it right here. And you can see my LSP client is complaining about it because, again, like, we have to specify to GCC that we want to do that. You can do that in a makefile. I've got one prepared here. And I realize that you can't really see that because my face is in the way. But this is the makefile. I just have a few basic C flags. I want warnings. I want to use GNU 99 standard. And then my rule for making our project here, you can see GCC, C flags. I include this thing, rolluxhound.c, and then I output it to a build folder. Now guys, this is really important. When you're doing systems programming and you're writing daemons, you have to put an extra D at the end. It's just what you want to do. It feels cool, it looks cool, it's like, it's cool, alright? It's cool. You're writing a real daemon. So in my makefile, I've specified that, we're building a real daemon. So, oops. If I go ahead and make this, give me a second. If I go to my build directory now, you can see I've got rolluxhound right there. So all I can do is hit make, and it'll run this command for me automatically. Now then, libnotify. So if you had a gaze at that that thing back there, like the Arch wiki page, it'll show you the example code of what we need to use for our project. So we need to initialize with libnotify. We've got to create a handle for the notification. Then we can show the notification. And then when we're done, we just clean up like this. Okay. So essentially, we're just going to go ahead and copy that. Not exactly, but we're going to copy it. And listen, copying and pasting code is totally fine. as long as you know what it does, and you could have come up with it on your own. So that's my opinion on the matter. So we're going to make a notify handle right here, and we're going to, if we have a look at this, and this is why I say, like, you got to understand what you're doing, because this notify init here, if you're really switched on, you might think, well, hey, that could potentially error, and you'd be absolutely right. If we go to the libnotify documentation, you can see here that this actually returns a boolean. So the Arch Wiki is kind of like skipping over the fact that that could actually error. So because we know it returns a boolean, we could do like libnotify init status. And what we can do down here, after we call notify init, so what we'll do now, I'll actually try and set that up before I notify. Because we want to get all of the sort of like, this could fail right off the bat out of the way before we set up the more deeper things. So interfacing with like the user level notification daemon, I'd probably prefer to fail on that first rather than fail on that after we do all of our system calls. So we're going to go ahead and do libnotify init status equals notify init. I think that was the one. Notify init. And then we're going to put the program title in here, so I'm actually going to define that as another global. Program title. Rolex sound up here. And if you've noticed, I'd like to do, my C stuff is in camel case. And I like to denote my globals with a capital, just so it makes it easier to see, but people have their own opinions on that. Now, like I said, my LSP is complaining, but really it's not a big deal, because GCC will link it correctly. If not, libnotify status, fprintf, standard error, initializing libnotify. And yep, you guessed it, it's time for another exit code. Cool. So now, if we get to this point, we can assume that we've initialized with libnotify, we've added all of our stuff to the watch queue correctly, and we're like ready to go. We're ready to go. So now we actually want to like do the notification. So if you go back to the Arch Wiki, you can see notification, they set this notification handle to the result of notify notification new. And then you can just go ahead and show that. And theoretically we should be off to the races. So what we're going to go ahead and do is get rid of this. And we're going to do notify handle is equal to notify notification new. And now we're going to do our base path, because this is, I'm pretty sure this is the title, like the title is the first argument, our notification message, and the last argument here is actually the icon that you want to show. So it can be anything. I'm just going to use the standard dialog information icon that's present in pretty much all Linux icon packs. Now, because this is a pointer, I'm just going to check, make sure this is not null. Notification handle was null, and this is not a critical error, so we can just continue off of that, but I just don't want to call anything, like, you got to be careful with checking your null pointers. So now we can do notify notification show, not new, show, and this takes our notify handle, and I'm going to pass it null. What actually does that second argument do? Error. Okay, I don't care. Okay, so this should, let me make sure it compiles. This should send us a desktop notification with libnotify. So we're over here on my main display, and I've actually moved my face because my notifications pop up on the right corner on this machine. But what we're going to go ahead and do, what I'm going to do is I'm going to go ahead and create a file called test.txt, write a whole bunch of stuff to it, and save it. Now we're going to set rolluxhound on it. So build rolluxhound D, because we're playing the big leagues, guys. We're writing Daemons. Going to be the next system D. Calling it now. So rolluxhound D, and we're going to set it on test.txt. So we're waiting for our event. Now if we edit this file again, you can see up here in the corner, it's popped up with file accessed. Now if we go ahead and write this file, a whole bunch of garbage, you can see we pop up with file modified and file written and closed. So just like what we want. Now the cool thing that I was going to show you before is you can actually use this on SSH identities, and I'll show you what I mean. If I set this here on SSH Eon ticket, that's one of my SSH identities, and I SSH into the machine that it supports, you can see here that it pops up in the corner with, my SSH identity has been accessed. So you can use this almost as a security thing. If someone tries to read your SSH identities, you can run it in the background, it'll pop up and let you know. So that's pretty sweet. We're going to go back to the code and we're just going to clean things up, do some signal handling, and it's going to be pretty cool. So the last thing that we're going to add to this program is a signal handler, and the reason we're going to do that is so we can shut things down correctly when we receive, and just clean up when we receive a kill signal. Because this is a daemon, it's not going to terminate normally, so we're going to have to send a signal to it to kill it. So what I'm going to do here is create a signal handler. And its one argument is going to be the signal. And here's where we're actually going to do exit with exit success, right? That we made all the way back at the beginning. So now, essentially, what we're going to go ahead and do is, printf. Actually, I won't do that to send error. I'll just say printf signal received cleaning up. And what we're going to do now is, if you go all the way back to this documentation for Inotify that we were talking about at the start of the video, you can see that there's a system call for RM watch, and we're just going to remove it from the watch list. Just we probably, like, the OS will probably do all of this for us, but it's just kind of good practice to get into the habit of it, right? So what we're going to do is, and this thing returns a success, so we're going to define a variable for us to hold this in, equals Inotify RM watch, and we give it our iEvent queue, and we give it the watch FD, which is this iEvent status here of our file. So we go ahead and check if close status equals -1, print to standard error, error removing from watch queue. And we're not going to exit because we don't care. So now we're going to go ahead and just close the iEvent queue like a regular file descriptor. Now then, you might, if you're really switched on, you'll be thinking, well, hey, these could not even be like legit file descriptors in the first place. There's a point here where this gets called, where these aren't actual legit file descriptors. And so, like, yes, you're right. But I'm not going to check them, because what I'm going to do is register our signal handlers after we make sure that that's all correct. And now this is the point that I was making before of, like, you want to fail at the higher levels before the meat of your program actually gets going. So now what we're going to go ahead and do is register our signal handlers. So the signals we really care about are sigabort, which is this one, sigabort, and we're going to give it our signal handler. We also care about sigint because that's Control-C from terminal. Give it our signal handler, and we care about sigterm. And the rest of the signals, you can look them up on like the Linux man pages. We don't care. These ones are going to be fine. So now if I go ahead and make this rolluxhound on, of course, got to give it a path. You can see here signal received cleaning up. And the fact that we didn't get this fprintf here means that we removed it from the watch successfully. And this is in 151 lines of code, pretty much. 151 lines of code. Which is pretty cool, guys. Like, if you think about the utility of something like this and everything that we've learned in 150 lines of code, it's pretty impressive. So what I'll do is I'll actually go ahead and clean all of this code up, I'll put comments in it to explain what everything does, and I'll post it to Pastebin or something and link it in the description below. Anyway, that was sort of my very first introduction to systems programming, where we wrote a very simple daemon that does something pretty cool. Let me know if you've come up with any ideas for daemons you want to write, and let me know how you went in the comments below. Thanks.